Hi, my name is Lauren Barger, and today I'll be presenting the Charged Tapes Lab for Physics 2212. In this lab report, I will be going over three main sections, consisting of the introduction, data, measurements, and observations, and finally, a glow script model I created to demonstrate the two charged tapes with the respective electric and gravitational forces. Let's begin with a brief overview of the lab. This lab allowed us to observe how electrons were transferred, as well as how to calculate the charge on a piece of clear tape. We were able to simplify this by treating the tape as point charges. Fundamental principles in the lab included Coulomb's law and Newton's second and third laws. Here's a brief overview of my results from the lab, but we'll get into that more in the next section. Some assumptions that were made before conducting the experiment were as follows. Ignore air resistance on a moving object. Treating the tape as though it were a point charge, with all the charge concentrated at the center of the tape. And finally, I assumed that each U-tape had about the same amount of charge, evenly distributed along the length of the tape. Now let's talk about the data, measurements, observations, and how they contributed to the calculations needed for the lab. Once I had created a charged U-tape, I began taking observations of how the tape interacted with objects of different charges. As you can see from the results, the tape was attracted to neutral objects, such as my hand or a desk. When the first U-tape was placed near a second U-tape, the two repelled. This was key to determining that the tapes had the same charge. To determine if the charge was positive or negative, I placed a negatively charged pen near the U-tape. The U-tape was attracted to the pen, indicating that the U-tape was positively charged. Before we move on, I want to talk about a couple of things. So if electrons had a positive charge and protons had a negative charge instead of how they normally are, nothing I observed about the interactions would change. Like charges would still repel each other and opposite charges would attract. All of the behaviors between the objects would remain the same. You can think of it as if I made a clock move counterclockwise instead of clockwise. Time would still behave the same way, but things are just flipped. Next, it's important to handle the tapes as little as possible so that you can keep the tapes as positively charged as you can. Once the tape touches your hand, which is a neutral object, the tape begins to neutralize as well. It equalizes with the charge on your hand and balances out. Next, I conducted the floating tape experiment. When running this experiment, I made sure to conduct several trials to calculate an average distance between the two tapes. This ended up being 0.033 meters. Then, I solved for a gravitational force. I then set this value equal to the electric force in order to isolate and solve for Q, which is the charge on the tape. This value is 1.5408 times 10 to the negative 8 coulombs. Next, I calculated the number of electrons on tape B by dividing the charge I just found by the absolute value of the charge on one electron. Then, I moved to the number of atoms on the tape. I began by calculating the area of the tape and area of an atom so that I could divide these numbers to get an approximate number of atoms on the tape. To get the ratio of electrons to atoms, I divided the number of excess electrons by the total number of atoms found. Finally, let's take a look at how all of this looks conceptually. The model on the right shows tape A and tape B as point charges. Tape A is shown as a red sphere, while tape B is shown as a blue sphere. The yellow arrow sticking straight up is the electric field created, while the green arrow shows the gravitational field. On my model, I also had the charge on the tape as well as the number of electrons on the tape displayed. Thank you so much for listening, and I'll see you next time for Lab 2.